Bingo. Okay, chapter 4, integration. I think we have 3 more chapters. 4, 5, and 6, we'll finish it up for the year. And then, of course, we got a huge chunk of review to get us to that. Oh, you know what this means, kids. Hold on. Julian.
Hello?
Why are you late?
School's usually being slow.
Ooh.
It just wouldn't open.
I don't think Schoology is one of our choices, is it? Wow, strike 2. That stinks. Sorry for those of you that are close to winning. Okay, so integration today. With integration, we're going to do something called an antiderivative. Obviously, if we've done derivatives, we want to be able to take the antiderivative or undo the derivative. The lesson today is loaded with some pretty common sense stuff, some basic operations, and a bunch of terminology. Excuse me. So we're going to find the general definition or general solution of a differential equation. That doesn't make much sense to you. It will by the time we're done. We're going to talk about something called an indefinite integral and make sure that you understand all the notation associated with that indefinite integral. We're going to come up with some basic rules on how to do this, just like we did with derivatives. So there's an analogy between what we did with derivatives and what we're going to do with antiderivatives. Then we're going to talk about how to find a particular solution, because notice the first one is a general solution. This one is a particular solution. I'll explain what that means. And then most importantly, we just got to make it through 2 more weeks. Okay? So let's try to be nice to each other. Let's try to get our work done. For those of you that have been slacking, this is your last chance to try and get things back up where it needs to be. For those of you that have been rocking and rolling, just keep rocking and rolling for 2 more weeks. Okay? Here we go. So, simple question. Let's suppose we have a function f of x is 3x squared. There is some function that when I took the derivative of that function, I got 3x squared as an answer. What is that function?
X to the 3rd.
Beautiful. Okay. Now, notice I've introduced some new terminology here. I'm calling this function that we just solved for capital F. So now we've got capital F, lowercase f, f prime, f double prime. So we're going to play with 4 different functions here. And we're going to go back and forth with all of those functions. Okay, now what do I mean by back and forth? Well, we have f, uppercase f, lowercase f, f prime, and f double prime. We're going to talk about going in this direction, which we've already done. Okay, so taking the derivative of f gives us f prime. The derivative of f prime is f double prime. But we're also going to talk about, mainly in this chapter, going backwards, going the other way, which we just did. We started with this function of f of x, and the question is, what does capital F of x look like in order to get that as an answer? Okay, does that concept make sense? Yes? Give me a thumbs up, please, if it does. If it does, then you'll have no problems with today's lesson. It's pretty straightforward. As I mentioned earlier, this is called an antiderivative. You can think of them as inverse functions. They undo each other. Okay? And that should be a fairly logical jump also, is that if you have a derivative, to undo the derivative, you would do the antiderivative. If you have the antiderivative, you would undo that by taking the derivative. Okay, now one thing we didn't talk about was most people follow the same approach when we talk about this. If we go back here, when you take the antiderivative of 3x squared, you get x cubed. Pretty easy. What we didn't take into account is something like that. What's the derivative of x cubed plus 7? Still 3x squared. What's the derivative of x cubed minus 12? Still 3x squared. So you realize that we get a whole bunch of different possibilities. It's not just it's not just x cubed, but it's x cubed followed by any possible constant because the derivative of a constant is 0. Okay. This is called a family of antiderivatives. There are an infinite number of solutions to the first problem that I asked you, which was, what function when you take the derivative gives you 3x squared? Now, does that make sense? Well, how do we know what that number is? How do you know that I wanted x cubed and not x cubed plus 7 or x cubed minus 12? We need a way to express that in general terms, meaning I can do that antiderivative. I know that there's some number after that. I just don't necessarily know what that number is. That number is, we're going to use C, capital C, to represent that constant. That constant is called the constant of integration. It's really important. Okay? So again, looking at this example, I'm starting with a function 2x. What function when you take the derivative of 2x would give me, what function when you take the derivative of it would give me 2x? That would be x squared, but then we throw that constant of integration on there to be x squared plus c. C can be any number. Now, weird things start happening when you deal with constants, like, for instance, what's c plus c? Well, you would think from algebra that c plus c would be 2c. It's not, it's just c. C is always c. You take a constant, you do something to it, it becomes another constant. What's the square root of c? Just c. What's c squared? C, etc., etc. Okay? How are we doing so far? Pretty straightforward? Pretty logical?
I have a question.
Certainly.
Can C be an irrational number, or not irrational? Can C be an unreal number?
An imaginary number?
Imaginary, sorry. Yes.
I'm going to give you two answers. One would be yes, and two would be we don't care because we're dealing only with a real number system. Okay?
Okay.
All right, so where am I? Okay, so find the general solution of the differential equation y prime equals 2. Okay, so I've got a function, it's a derivative. The general solution would be, now this is what a differential equation is. A differential equation is basically doing an antiderivative, going backwards. What function, when I take the derivative of it, gives me 2? Okay. Fairly simple question, and it would just be 2x. However, like I mentioned already, there's an infinite number of solutions on there, so we have to stick a plus c on there. One of the many common mistakes that people make when they first start dealing with antiderivatives is forgetting that plus c term. Okay? Problems? Pretty easy, yes? Okay. What's going to happen is that now that we've done derivatives, and I'm going to ask you to start doing antiderivatives, you're going to get confused between the two. There's going to be a time when I ask you to take an antiderivative and you're going to take the derivative, or vice versa. You got to be careful to keep track of all of these. It gets worse later on, like when we start talking about the trig functions. Okay? But again, I'm going to go slow and make sure you follow me here. Okay, so now we got some notation. We have a new symbol. It's that squiggly mark. Okay. So you want to practice at some point making that thing. And how you make it is up to you. It's got to be legible, though. Some people just kind of do one of those. Some people have the big, fancy, swirly, perfect-looking thing. I've seen people do crazy things like that. That's probably not very good. That doesn't really represent an integral. That's just you showing off your artistic abilities. But you will have to practice a little bit to get that squiggly thing under control. Okay, so that's a symbol for an antiderivative. Just like we had primes for derivatives, that's the antiderivative symbol. The thing that you're taking the antiderivative of is called the integrand, the function, in other words. And you notice this little dx pops up. That dx is very important. It's the second most common mistake that people make when working with antiderivatives. They forget to include the dx. Well, why is the dx there? I'm going to give you a simplified version. The dx, which is called the variable of integration, tells you which one of these things is a variable. We've talked a little bit about that already, especially when we were doing the optimization problems. We had problems involving w, s, h, and x. Of those variables, of those letters, only one of those is the variable. The same thing is true here. When we're dealing with basic f of x functions, it's pretty easy. X is our variable, let's go from there. But it will change later where we're taking an antiderivative of something like xyz dx, meaning that x is the variable, y and z are numbers, and so we know how to treat that. The capital F is the actual antiderivative. And then C we talked about already is the constant of integration. All of those components are necessary for a well-written antiderivative. Okay? The symbol, the function that you're taking an antiderivative of, what's called the differential or the variable of integration, the actual antiderivative, which you'll get better at through practice, and then the constant of integration.
Does the variable of integration just stay as dx, or will there be an actual, another variable in there?
It can change depending on the problem. Okay, I think this will answer your question. For instance, I can give you a problem like this. Okay, does that make sense? It's not always going to be x. Or, like I said before, now, how do I treat this last one? Well, this would be my variable. These are just numbers. Okay, and it's similar to what we did before when we were taking, let's say, the derivative of wx with respect to x. So this would be the derivative with respect to x of this would just be w. The same thing is true here. Here we're taking an antiderivative of this mess with respect to x, where x is my variable. Does that answer your question?
Yes.
Good. Anybody else before we move on? Beautiful. Okay, that whole process is what's called an indefinite integral. At this stage, I'm not going to really tell you why it's called an indefinite integral until we talk about a definite integral. So it's easier to define an indefinite integral once we've talked about definite integral, which we're not ready for yet. So you'll just have to trust me. And notice that I will use the terms antiderivative and indefinite integral interchangeably. Okay, so now we need some mechanics. How do we do it? Okay, what process did you go through? Well, when we started with something easy like 3x squared, you didn't have to be a rocket scientist to figure out the function, but what happens when it gets more complicated? So, I forgot about this. Okay, we'll continue on that in a second. I talked about the fact that the antiderivative and the derivative are kind of like inverse functions. So in this case, what I'm doing is I'm taking the antiderivative of a derivative and ending up with the original function. Does that statement make sense? Yes or no? Kind of?
Yes.
Okay. Notice that there's a C at the end of this because the last thing I did here was take an antiderivative. I guess I keep forgetting you guys can't see when I point. This is a derivative. When I take the antiderivative of that, I end up back at the original function, but I have to have a plus C on there because I did this second. Okay, does that make sense? Maybe that helps. Or maybe that confuses you. But again, what I did is I took a derivative first, then an integral. What happens if I switch the order? Okay, so the best scenario I can give you is something like this. This would be the comparison I would give you here. Okay, in the top one, I'm taking x and squaring it first, then undoing the squared function with a square root function. In the bottom one, I'm doing a square root first, then squaring it. Notice, this would be plus or minus x. This would just be x. Okay, that's relevant in a second. Okay. Because what if I do it out of order? What if I do the integral first, then I take the derivative? There's a subtle point here that needs to be talked about, and that is, why is there no c on the other one? On the one I just did, where'd the plus c go? And the answer is, it disappeared because the derivative of a constant is 0. So when I did this part first, okay, the antiderivative of little f would be capital F of x plus c. And then when I take the derivative of that, the derivative of capital F is lowercase f. The derivative of a constant is 0, so it disappears. As opposed to the top one, I take the derivative of f, I get f prime. I take the antiderivative of f prime, I get back to the original function, but because the last thing I did was an integral, I have to have that plus c on the end of it. Okay. It's a subtle idea that pops up occasionally in some of the things that we're going to talk about in the future. I would say the best way to handle this is to ask yourself, what did I do last? If the last thing I did was an integral, then it needs a plus c. If the last thing I did was a derivative, then no plus c. Okay, so let's get away from the concept stuff and let's do some practical application here. So we'll start with f of x. F of x is equal to x cubed. What's capital F of x? In other words, what function, when you take the derivative of it, gives me x cubed? If we want to practice the notation here, I'm asking, what is the antiderivative of f of x dx? Or what is the antiderivative of x cubed dx? What derivative, what function, when you take the derivative of it, gives you x cubed?
1/4 x to the 4th.
Perfect. I didn't see who was talking.
There's Madison.
Nice job, Madison. For those of you that didn't answer, either because you're too bashful to talk or you didn't understand what's going on, do you see why that's the correct answer? If I take the derivative of this, I will end up at x cubed. Bring the 4 down, reduce it by 1. 4 times 1/4 is 1. 4 minus 1 is 3. Good. Any problems there? Okay. In that case, I'd like to generalize this. What would be the rule to get that answer? In other words, what if I had x to the nth? What would the antiderivative of x to the nth be?
I'm going to guess here. I'm going to say n minus x to the n minus 1. x to the n plus 1. And then the number in front of the x would be 1 over n plus 1.
1 over n plus 1 or 1 over n?
1 over n plus 1.
This?
Yeah.
Okay. Not bad. I'll give you that. You forgot the plus c. That's okay. Is she right? Well, let's see. If one thing we do know is we know our derivative rules. So the question is, what is the derivative of that? Okay, well, the derivative rules are you bring the exponent down. So that would be n plus 1 over n plus 1. Whoops. And reduce the exponent by 1. So n plus 1 minus 1 is n. And the derivative of c disappears. That's equal to 1, and sure enough, we get x to the nth. Well done. And I have that written out for you. Staying with the analogy I mentioned earlier of comparing this to derivatives, what we just came up with is what would be comparable to our power rule from derivatives. Okay. Now, personally, I'm going to change it a little bit. Here's the way, this is the true calculus equation, works great. I'd like to take it a different approach to it. Okay, and you'll see that in red. Raise the exponent by 1 and multiply by the reciprocal of that new exponent. Okay? Now, what's the difference? Well, there is no difference except using the method in red, you don't have to worry about taking 1 divided by whatever. So for instance, if I had x to the 1/2, what's the antiderivative of x to the 1/2? Okay, so raise the exponent by 1, so that would give me x to the 3/2. And if we used Alex's, I think that was Alex, right? We'd have 1 over 3/2, which then I have to deal with, well, a fraction over a fraction. This method is easier because you just take that new exponent and you take the reciprocal. Multiplying by the reciprocal, same thing as dividing by the number. Whoop, made my own mistake. Plus c, don't forget the plus c. Okay, so this is the actual formula, the fancy schmancy calculus stuff. This is the more practical method we're going to use over and over again. Raise the exponent by 1, multiply by the reciprocal of the new exponent. New exponent, not the old one. Okay? So this will get us through basic antiderivatives. And because that's flashing, you know it's important. The next slide is going to make you either very happy or very upset. It probably won't make you very upset, but it'll probably make you pretty happy in that there is no product rule, quotient rule, or chain rule for integrals. Now, having said that, many of you will try it at some point in time. You're going to take an antiderivative by using a quotient rule. It doesn't work. Now, this is nice, but the flip side is we have to come up with other methods to be able to do this. Okay? So just because there's no product rule doesn't mean we can't take the antiderivative of some product. We just have to do some other methods. The other methods can get kind of ugly. The BC people in the crowd, where are you at? Where are my BC folks? Did you guys get to antiderivatives in BC?
I didn't, no.
No? Jackie, you did?
Yeah, I did.
Did you get to UDUs? Does that mean anything to you?
No.
Oh, okay. So you guys are in for a treat. For the rest of you, that's one of the techniques that we use with antiderivatives, which is called UDUs. No need to worry about it now. We'll worry about it later. All right, so here are our trig antiderivatives. which for the most part, if you look at them, they should make sense. We know right now that the derivative of sine is cosine, therefore the antiderivative of cosine is sine. First one's easy. Done. What about the bottom one, though? Well, we know that the derivative of cosine is negative sine, so we cheat by putting the minus sign on the other side. The same is true. Now, notice these aren't the other four. These are some wonky things that popped up out of nowhere. Where did those come from? Well, look at the other side. There's tangent, there's secant, there's cotangent, there's cosecant. So all 6 of them are represented. What we don't have on this slide is, what is the antiderivative of the tangent of x? What's the antiderivative of cosecant? That comes later. Okay, this is just simply taking the derivatives we already know on the right-hand side and coming up with the left-hand side. The biggest problem for you guys is going to be not knowing the values, but it's in particular these 2 guys is going to be screwing up the minus sign. Many, many years ago, back when I was in college, somebody showed me this stupid golf thing. And at the time, I thought it was really dumb. You probably will also. But it helps me remember the difference between cosine and sine, which one gets the minus sign. I'll show it to you. You may think it's silly, and you can just forget about it. But for some of you, it might help. It's helped me for the past X number of years. And it goes something like this. Suppose I want to take the antiderivative of the sine of x. I know that sine and cosine are cofunctions, so this is going to be the cosine of something. Okay, cosine of x, actually. But if you imagine the antiderivative sign being a golf club and the dot on the I being a golf ball, when you hit that golf ball, it travels so fast you can't really see it. It just leaves a blur. Again, it's really dumb. But if it helps you remember which one gets the minus sign, great. Okay, you got these 6? Are we good? Speak now or forever hold your peace. Okay, so let's find an antiderivative. Now all of a sudden I changed things a little bit. I put numbers in front of it. Well, how did we deal with numbers when we did derivatives? Well, we talked about how to find the derivative. Way back when, we talked about how to find the derivative of x cubed. 3x squared. Done. Then we said, oh, wait a second. What if I want to find the derivative of 4x cubed? Well, we learned that that was just the derivative of x cubed times 4. So we just leave the 4 out in front. The same applies for antiderivatives. So here's my solution. And I broke it down into a whole bunch of different steps. However, you probably, as you get better at this, won't have to do this, but the rule is the same. The antiderivative of 8x cubed is the same thing as 8 times the antiderivative of x cubed. The antiderivative of 7 sine x is the same thing as 7 times the antiderivative of sine of x. Then take the derivative of each individual part, multiply your answer by the numbers out in front. So the antiderivative, as we already talked about, of x cubed is 1/4 x to the 4th. 1/4 times 8 is 2. That's where the 2 came from. Antiderivative of sine, using the stupid golf thing, is negative cosine. But again, I've got a 7 sitting out in front, so it becomes negative 7 cosine of x. And then don't forget the plus c. Now, how important is this plus c? Let me explain it to you this way. Anytime you have an integral on, let's say, a free response question on the AP test, that free response question is worth 9 points. It is common for that little c to be worth 1 point of those 9. That doesn't seem like a big deal, but you need to understand that the entire free response portion of the test is only 54 points. Therefore, that 1 point is crucial. And it requires virtually no work. All you have to do is just remember, I'm taking an antiderivative. I need to put a plus c at the end of it.
Sorry.
Yo.
If you take the integral of both, so you took the integrals separately, 8x cubed and 7 sine x, wouldn't there be a plus c for both of them?
Very good. Yes. So I'm going to answer your question in a roundabout way. So what Noah is saying is if I took this initial equation, couldn't I do it this way? Right? And if I take this antiderivative, I get 2x to the fourth plus c minus 7 sine x plus c. Ooh, and don't get sloppy. That should be in parentheses, right? So you're saying to yourself, Noah, well, isn't c minus c 0? However, one of the things I talked about earlier is it doesn't matter what you do to c. C is going to be c. Okay? C minus c is c. C plus c is c. C squared is c. It's all just a constant. Would it change the numerical value? Yes, but we don't care because we're just representing that numerical value by a constant. Make sense? Okay. There's nothing wrong with this. In fact, you could do it this way that I wrote it. You don't have to. It's entirely up to you. Okay, doc. Let me stop for a second. How we doing? Is this making sense? Give me a thumbs up if it does, please. Okay, pretty straightforward. Good. Just some notes on approaching problems, just like we did, like it says, with differentiation. Okay, we took equations, we rewrote them into some, so instead of taking the derivative of square roots, we would write it as raised to the 1/2 power. The same is true with antiderivatives. Okay, so let's take 5 minutes. Okay, I got us at 35. Noah, pick a number 1 through 5, please.
4.
4, and then pick a number 1 through 6.
5.
Lexi.
Oh, I don't really know if I did this right.
That's okay. We still love you, even if you made a mistake.
So I was a little confused.
I understand.
I got it wrong, but I got 12 fifths x to the 5th minus 20 thirds x to the 4 thirds minus 1/4 x to the negative 4th.
You got anything else for me?
Oh, plus c?
Yeah. Okay, so let's go to JT. How'd she do?
That's what I got too, but I'm not sure if that's right.
Wow, you guys are so negative. Holy crap.
I don't.
You have the exact same answer she has, but you need to throw in the fact that I don't know if that's right. It's probably wrong.
I'm confident in myself. Right now,
I'm
so
never going to
I
get
don't-
into college. I'm never going to have a good job. I'm going to live in a refrigerator box eating hot dogs out of garbage cans. My life is over. Well, if you're going to be doing that, so's Lexi, because then she got... Anybody else want to chime in here? Anybody else?
Not what I got.
What's that, Noah?
That is not what I got.
Oh, so maybe Noah's the one that's going to be eaten out of a garbage can. Let's find out. Lexi, can you talk me through the steps that you followed? Did you do anything? Did you rewrite this first before you did it?
Yeah.
Okay, so I'm assuming you did 12x to the 4th minus 5x to the 1/3. Get that out of there. Plus x to the negative 5th.
Yeah.
Okay? So then what?
Then I split it up how we did it in the last problem.
I like it. Go ahead.
I don't know what's the line thing called?
I don't think it, I've been wondering for years. I don't think it has a name. I just call it the squiggly thing.
Okay, so squiggly thing 12x to the 4th dx minus squiggly thing 5x to the 1/3 dx plus the squiggly thing x to the negative 5th dx.
Okay, so then if we take this first one, raise the exponent by 1 is the 5th. That's good. And multiply it by the reciprocal. So the reciprocal 1/5. Okay, so I agree with this. Let's see. 1/3 plus 1 is 4/3. 5 times the reciprocal of 4/3 is 20/3. Okay, I agree with that. And then here's a common mistake, kids. -5 plus 1 is -4, not -6. Good job, Lexi. So that's a -4 multiplied by the reciprocal. Notice how she was clever enough to turn that into a minus sign. Boom, and then got the plus. I agree with what you have here. So there is hope for the two of you.
Perfect. Glad to hear it.
Yeah.
Multiplying by the reciprocal, wouldn't that get 15 over 4? That was the only difference I had in answers.
Yeah, I got 15 over 4 as well.
15 over 4.
Me too.
Here?
For like the second term.
The second term?
20/3.
That would be 4/3 would be oh yeah, I missed that. Sorry. Oh. Because that would be 5 times. No. Oh, the reciprocal of 4/3, 3/4. There you go. Now I talked myself out of it. Thank you, Noah. Oh, JT, guess you're going back to the garbage can, buddy.
I guess so.
Yeah, that's all right. Well, maybe. We'll see what we can do. All right. So, number 1, a lot of places to make mistakes. Number 2, you're going to have to shut off your derivative brain for a while. Because the derivative brain wants you to bring that exponent down right away. With antiderivatives, you got to do some work to it before you bring it down in front. Okay? Boy, that looks like a mess there. Let's move on. Okay, so let's think about what we're doing here. So I took an antiderivative of some function and I get another function and there's a plus c on the end of that. So let's suppose I take the antiderivative and I get as an answer x squared plus c. Okay, and we can talk about what function would do that, but I don't really care right now. I just want to look at the fact that we get this general solution x squared plus c. Well, what does that mean? If you think about it from a graphical standpoint, I've got an antiderivative that gives me an answer of a parabola with a numerical term at the end of that. So the question is, what's the difference between something like this and something like this? How do those two graphs differ?
One of them is like the y-intercept is at 2, or 2, and the other is at -3.
Perfect. All it does is it takes this function and slides it up and down. Okay? That's it. That's the only thing a numerical value at the end of a function is going to do. And so this infinite number of families that we get when we solve the antiderivative is just an infinite number of parabolas stacked up on top of each other, sliding up and sliding down depending on what c is. What we want to do is we want to find that one particular parabola. Okay? I've got in my mind, I want that one particular parabola that satisfies some conditions. I can't do that if I don't know what the conditions are. And so that's what we're going to do now is go from a family of solutions to what's called a particular solution. Only one answer. Okay? So, general solution first. Okay, so when I take the antiderivative of that, we've done enough examples already. That would be x to the -2. You take the antiderivative, you get. Okay, so we start with this. And what I did to change things here is I threw in an initial condition. I want the one particular answer that satisfies that condition. And in fact, if I go back to all these parabolas, I want the parabola that passes through a particular point. Okay? And in the example I have here is, I want the function, they're not parabolas now, but I want the function that passes through the point 1, 0. Of those infinite number of functions I have stacked up on top of each other, which one goes through 1, 0 is what I'm asking. Okay? So how do we do that? Well, we get that set up. You take an antiderivative, which we talked about already. That's x to the negative 2, raise it by 1, multiplied by the reciprocal, and I get that. Okay, so this is a general solution of the equation, an infinite number of functions stacked up on top of each other. But now, I need to get this puppy involved. Well, what does that mean? That means when x equals 1, the function equals 0. Don't make this more difficult than it's supposed to be. It's just a plug and chug. Notice in this expression, I've got 3 variables, x, y, also known as f of x, and c. I know 2 pieces of information from up here, plug and chug and solve for c. Okay. So there's my general family of solutions. You didn't necessarily need to do that last step, but I threw it in there just to show off. And then, on the next slide, I find the particular solution by plugging that in. So c equals 1, which gives me the final answer of that. More important than the answer, I want you to be sure that you understand the concept of what we're doing here. And I don't want to keep repeating myself over and over again. So do you understand what I just did? Do you understand the difference between a general solution and a particular solution? Okay, good. I see everybody's, I see most people's heads shaking. So I'll assume we're good to go. This idea of finding the particular solution is what's commonly referred to as a differential equation. So now we've got antiderivatives. We've got integrals, which are synonymous. They're the same thing. But if we combine finding the particular solution, we now throw in what's called a differential equation. There are entire courses in college where you do nothing but do differential equations. Okay? It's a good course. I took it in college. It was fun. Okay, so let's try this one. We're solving a differential equation. What I'm asking you for is I want to know what f of x is. Give it a shot.
Mr. Reedy, I have a question.
Uh-huh.
So, the point that's given, like whenever we get f of a number is equal to another number, is that always going to be like the vertex of the graph, or is it just going to, no? No,
it's just a point that the graph passes through.
Okay.
It's nothing fancy. It's just a, because I've got all these things that are stacked up on top of each other. Which one of them passes through this particular point floating out here in space?
Oh, okay.
Okay. And sometimes that point will be a y-intercept. Sometimes it'll be the origin. Who knows? It's just some value.
Okay, that makes sense. Thank you.
Yep. Okay, I'm going a little fast, I know, but I want to be sure to get through this slideshow before we call it quits for today. I'll ask for a volunteer before I volunteer someone. Does anybody think they have a solution?
I think I do.
Go, Noah.
Sorry, I was muted. Capital F of x equals 3x cubed plus 2x squared minus 7x plus c.
Hold on, I'm not that fast. Go ahead.
Plus 2x squared minus 7x plus c.
Okay? First of all, that would be lowercase f of x, because when you take the antiderivative of f prime, you get back to the original function. How do we feel about his antiderivative so far? Good? Did you do that part correctly? All right. Noah, you're half done. What's C?
The constant?
Yeah.
Okay.
Oh, I'm sorry. That was your answer. What's the numerical value of C?
Oh, I gotta plug it in. I haven't done it.
Jack, what would I plug and chug into Noah's antiderivative to find C?
You would plug 5 in for. Wait. Yeah, you would plug 5 in for f of x, and then you would plug 1 in for all the x's. And I think you would get 7 for c.
I got negative 30. Or negative 33.
3 plus.
I got 7.
Okay, hold on. 3 plus 2 is 5. Subtracting 5 from the other side would give me 0. Minus 7. Yeah, I got 7 also. So therefore, f of x would be 3x cubed plus 2x squared minus 7x plus 7. Done. Okay. So Noah, what you had originally in red was the family of solutions. Infinite number of cubics stacked up on top of each other, but we wanted the cubic that passes through the point 1, 5. So Jack was kind enough to help me out by doing that, and we found that that happens when the C term is equal to 5. And now this final thing is our particular solution, also known as a differential equation.
When does the capital F come into play?
Remember, we've got this order now. Okay. Going this direction is derivatives. Going this direction is integrals. Okay, so in this particular problem, we started with f prime, so the antiderivative of f prime takes us back to lowercase f.
Got it. And is there no, we don't have to indicate that it's f of 1 that got us that c value?
No, he indicated it by doing this here, by plugging 1 in for x and c and 5 in for the function f of x.
Okay.
Okay, if you prefer, you could write this as the point 1, 5. Okay, any other questions? All right, let's see what else we got here. Ooh, okay, I'm going to do this one because it's a little nasty. But look at how much fun this is going to be. So here's what I did on this one. I thought, time to strap on the big boy pants. Not only did I start with a second derivative, but just because I was feeling saucy, I threw some trig in there. In order to get all the way back to f, because remember, we're starting here with f double prime, and I'm going to go f double prime all the way back to f, I needed 2 starting pieces of information. Okay, so here we go. The antiderivative of f double prime is just f prime. The antiderivative of sine is negative cosine, so this becomes negative 3 cosine of x plus 5 sine of x plus c. Now I use this piece of information. When x equals 0, f prime of x equals 2. So this becomes 2 equals negative 3 times the cosine of 0 plus 5 times the sine of 0 plus c. So that's 2 equals negative 3 plus 0 plus c. So c is equal to 5. which means that f prime of x is negative 3 cosine x plus 5 sine of x plus 5. I'm not going to do the last step because I think you're with me now. So what I would have to do then is take the antiderivative again to go from f prime back to f. I'd get an antiderivative, and then I'd have to use this chunk of information in order to solve for that last c term. So notice I'm going to get two c terms. I get one c term here for the second derivative and another c term for the last step. The trig problems get a little bit weird because you can just keep doing antiderivatives over and over again. When we work with polynomials, you take a derivative, eventually it disappears. When you take an antiderivative, it keeps growing. With trig, it just keeps flipping back and forth between sine, cosine, sine, cosine, sine, cosine. Does this make sense? Is anybody incredibly distraught that I'm not finishing it? No? Good. Day 37. It is important that we try to save the cat population and that some of you stop doing bad math. Tomorrow's lesson, we'll talk about how to save a puppy's life by not doing bad math. Okay? Questions? Outstanding. Let me stop my recording here.